For many reasons, nematode management is not and should not be a matter of simply identifying a specific pest and then applying a chemical nematicide that is effective against it. There are so many situations for which no safe, effective chemical nematicide is available. Most chemical nematicides are relatively toxic, so they are hazardous to people, pets, and other animals if handled carelessly. Most nematicides are environmentally risky because of their toxicity. Unfavorable environmental conditions and/or events can make all nematicides less effective than expected. Nematicides are expensive. Many cultural practices can affect how seriously nematodes affect a planting and how effective nematicides are if they must be used. Carefully combining many of the following practices into an integrated nematode management program often will help keep nematodes below damaging levels and improve effectiveness of nematicides if they are available and must be used. In the first video, I mentioned about how this boxwood on a Navy base had nematodes. So what do you do about it? The best solution is to replant with nematode-resistant varieties or plants that are not susceptible to nematodes. I'm Dr. DeBusk, and in this video, I will discuss nematode management strategies. Preventing a nematode problem is far better than trying to treat one after it is established. Many serious nematode pests are widespread, but some are quite limited in distribution, either from one region to another or from field to field. One can avoid carrying serious nematode problems into uninfested land by knowing that nematodes are spread in contaminated soil and plant parts. Good sense dictates working in areas that are not infested with nematodes before moving to those that are infested, to avoid carrying contaminated soil or plants to the uninfested field. Ornamental cuttings to be rooted should be taken only from uninfested plants or portions of plants from above ground that have never been rooted in potentially contaminated soil. This prevents propagating populations of nematodes that might seriously reduce growth and might cause the plants to be unfit for shipment to many potential markets because of quarantines. Quarantine is environmental action taken to prevent importing a pest into a previously uninfested area, usually by controlling movement of contaminated soil and plant material. Crop rotation is a very old practice for reducing soil-borne problems. Many nematodes, soil-borne disease organisms, and insects can reproduce and survive on only a few plants. Repeatedly planting a field with the same crop without interruption will enable any organisms to reproduce successfully on that crop to continue to increase. Rotation to non-host crops may interrupt nematode reproduction and allow natural mortality factors to reduce their numbers. By carefully planning the sequence of crops to be planted in a particular field, it may be possible to avoid excessive buildup of pests of all the major cash crops in the cycle. In a few instances, it is even possible to include a crop in the rotation that will help control pests that have built up in preceding crops in the cycle. For instance, hairy indigo can be planted as a summer cover crop to reduce numbers of sting and root knot nematodes, and pangola digitgrass is used to control burrowing and root knot nematodes in vegetables. Other popular cover crops include sorghum sudan grass, different grains such as oat and rye, many grasses, marigold, cowpea, and some tropical legumes such as sun hemp and velvet bean. The many kinds of plant nematodes in Florida complicate selection of rotation crops because crops that reduce some species of nematodes may favor the increase of others. Despite the difficulty, a good rotation program should be a basic component of land/crop management plans because of the multiple benefits that can be derived from it. Crop root destruction gets far less credit than it deserves as a nematode management practice. Nematodes, soil-borne diseases, and many soil-borne insects will continue to feed and multiply on crop root systems as long as they remain alive. When soil temperatures are high, each month that a root system continues to live represents an additional generation and potential increase of about tenfold for many nematodes. Even when soil temperatures are gradually declining, a 2-month period may support at least one additional generation. Therefore, destroying root systems as soon as a crop is finished can stop nematode reproduction and should encourage their decline through natural mortality. Flooding may sometimes be used to help reduce numbers of nematode pests. It is practical only where the water level can be controlled easily and maintained at a high level for several weeks. Where flooding can be practiced, alternating periods of about 2 or 3 weeks of flooding drying, and flooding again are apparently much more effective than a continuous period of flooding. The soil should be worked during the periods of drying to increase aeration and drying of soil and to prevent weed growth while the soil is exposed. Flooding probably kills nematodes by providing a long period without host plants rather than by some direct physical effect on the nematodes. It is also important to consider the possibility that flooding with contaminated water may actually spread some soil-borne pests such as nematodes. Fallowing is leaving a field with no plants on it for a prolonged period to starve nematodes or other pests. Most nematodes will decrease after a period of time without plants on which to feed. For fallowing to be effective, the field should be cultivated regularly to prevent growth of weeds and to expose new portions of the soil to the effects of drying and heating. If weeds are allowed to grow in fallow land, many kinds of nematodes may be able to survive and reproduce on the weeds, making the practice ineffective. A promising technique is the use of heat to decrease not only nematode densities, but also other harmful organisms and weed seeds. Solarization involves the covering of the soil with clear plastic. Transparent plastic sheets allow short-wave radiation from the sun to penetrate the plastic. Once the light passes through the plastic and is reflected from the soil, the wavelength becomes longer and cannot escape through the plastic. The trapped light facilitates heating of the soil to temperatures detrimental to most living organisms. Thin, transparent plastic sheets appear to achieve the best results. The plastic has to be sealed to prevent air movement underneath the plastic, which prevent temperatures from rising sufficiently. Soil temperatures only rise to detrimental levels in the first 10 to 30 centimeters of soil. The soil should remain covered for a minimum of 4 weeks during the summer to reach optimum temperatures. Cloud cover and rain limit solar radiation and may diminish the success of solarization. Resistance of plants to a specific pest is usually the least expensive and most effective means of minimizing losses to that pest. However, successful use of varietal resistance requires knowing the extent and limitations of the resistance and which pests are present in a particular situation. There are nematode-resistant varieties of tomatoes, soybeans, southern peas, sweet potatoes, cotton, and tobacco available for use in Florida, but each of these varieties has resistance that is effective against only 1, 2, or at most 3 species of nematodes. None are nematode-proof. It is necessary to know the pest species present in a field to select a variety with the appropriate resistance. In addition, varieties with the appropriate resistance must be adapted to cultural conditions and requirements of your area. Another limitation to using nematode resistance as a major management practice is that high temperatures often weaken or destroy the resistant effect. Tomatoes resistant to root knot nematodes may not be able to limit nematode reproduction or effects if soil temperature is hotter than 81 degrees Fahrenheit. It also is still necessary to use other methods to control any other nematodes that are present, because the resistance against 1 or 2 species is not going to affect the ability of any other nematodes to injure the crop. Many different bacteria and fungi that are nematodes' natural enemies have been isolated from nematode populations apparently being kept at low levels by the bacteria and fungi. Nematologists have been able to use some bacteria and fungi to reduce populations of some kinds of nematodes under laboratory conditions, but successes at the full-scale field level have been few. Most organisms recognized as promising for biological control of 1 or more nematode pests are quite specific in which nematodes they will attack, have been very difficult to culture in sufficient quantities to be useful for field application, or both. The conditions under which each is most effective are often quite specific and limited. Commercially effective biological control as a means to reduce the effects of nematodes on any cultivated crops may still be many years away. There is a bionematicide called Melicon WG that contains live spores of a fungus that can be used, although it is not as effective as chemical nematicides. Although it is difficult to use biological control commercially, there are ways to enhance the natural enemies already present, such as through the addition of organic amendments such as compost and mulches. Amendments improve the soil environment to aid biological control, benefit general plant health by helping with water retention and providing additional nutrients, and affect nematodes directly and negatively through detrimental decomposition products. The impact of organic amendments on nematodes is often inconsistent and unpredictable, and they mainly increase a plant's health in order to tolerate nematode damage more. Nematicides are chemical products intended to reduce nematode densities and protect crops from damage. Nematicides sometimes can be very profitable when used correctly in appropriate situations. However, their effects are almost universally short-lived, so they should be used in conjunction with other practices that minimize nematode reinfestation of a planting and reproduction. There are two types of nematicides: fumigants. Fumigants, broad-spectrum pesticides that move through the soil as a gas, and non-fumigants, granular or liquid products that affect only nematodes and, for some products, insects. Many nematicides are expensive and require specialized equipment. Examples of fumigants are 1,3-dichloropropene, telone 2, metam sodium, and metam potassium. Non-fumigant nematicides are often less effective than fumigants, but less costly to apply. Non-fumigant nematicides work by coming into contact with nematodes in the soil, or if the product has systemic activity, by being taken up by the plant. Examples include fluopyrim, aldicarb, and oxamil. In summary, nematodes can be difficult to manage once you know that they are the problem. It is recommended to use an integrated approach to manage nematodes, which may include resistant cultivars, cultural control, and mechanical or physical strategies. Nematicides should be a last resort since nematicides are not labeled for all plants affected. They can be expensive and provides a greater risk to the applicator and the environment.